So happy Tuesday here. We're kind of transitioning what part of the course we are in here. In the first 4 units, if you remember, we did a fair amount of computational theory. We looked at Backus-Naur form for grammars, context-free grammars, and parsing. We looked at finite automata sort of stuff. And those are kind of traditionally programming or not theory course kind of topics. Sometimes they're in a programming language course too. Then after Unit 4, we really went into what we traditionally call a programming languages course. We looked at topics and how they're applied in different programming languages. So control flow, composite types, classes, type systems, all that sort of stuff, variables, reference pointers, and that sort of stuff. And we were basically looking at what we would call imperative programming languages that you're familiar with. So I would guess a lot of the code, even though we were looking at a couple different languages, wasn't that hard. You were able to kind of figure it out, hopefully, or look at examples in, Java or Python or JavaScript, for example, because they all kind of have the same underlying, they all have loops, they all have if statements, they all have arrays or lists, they all have, types there. Now, the last couple of weeks of the course, we turned back to theory. We learned Turing machines and computational theory. We talk about space and time complexity. This Unit 10 is kind of a transition. This is usually in a programming languages course. We look at some different types of programming languages. We look at functional and logical programming languages. And what I think you'll find is these languages are different in a lot of ways from what you're used to. And so it'll be a little harder to transition or understand these languages here. There'll also be languages that you probably haven't never heard of before, possibly. But and again, they're not that widely used. They're used a lot in academia to research or explain topics, develop new programming languages. But we do see a lot of spillover to other languages. So a lot of the list processing that's in Python, a lot of the Lambda functions that we saw recently when we looked at Unit 9, those sorts of stuff come from functional programming languages here. So it's kind of fun to look at these non-imperative programming languages and how they're set up and how they work. So that's what we're going to be doing for Unit 10, is looking at these what we call non-imperative programming languages. So as far as the readings go, I'm just going to, again, I've been looking at 2 textbooks for the middle of this course, Sylvester and Scott, and these both have units on functional programming languages and another unit on logical programming languages. Like I say, this is pretty common in a programming language course here. I'm just going to do a brief kind of overview of these chapters, kind of lay out the framework, and then we're going to jump into our AI prompts and start working with examples. One thing I want to kind of note is what languages these books use, because we'll have to pick which languages we are going to want to use here. And again, this talks about this. You said the previous chapter focused largely on chapters focused largely on imperative language. This chapter, the current chapter next, will emphasize functional and logical languages instead. Imperative languages are far more widely used, industrial strength here. But again, these, of course, functional and logical languages generally deal with, this kind of strange research or strange kind of stuff. So we're going to look at that. They go over, again, these books love to go over history. So go back to the 1930s with Turing and that sort of stuff and work with this. They talk about lambda calculus, here, and Church's theorem and this idea of lambda calculus is actually developed before. This is a mathematical concept, and it was later applied to computing here. This functional calculus. Lambda calculus is kind of like a math. In math, we have functions, but then this is applying functions to functions where we treat functions just like anything else, and we can apply functions to functions here. And they come from the lambda, the Greek letter lambda, which is here. But again, we usually don't write the Greek lambda, so we sometimes will write out the word lambda here. This talks about, again, first-class functions. And what this means is that functions can be just like variables or numbers or whatever they are. They're just like anything else. You can pass them as parameters. You can, set their values. You can move them. They're just like anything else, like a string or a integer or a variable type. We work a lot with recursion here. We generally in functional languages do not have any sort of loops. So everything has to be done with recursions for this stuff. So, okay. Then this author talks about Scheme, a well-known research language or functional language, and starts writing Scheme. Scheme has kind of a weird functional notation. It uses prefix notation. I don't know if you've seen prefix notation, but rather than saying 3 plus 4, where the operator is between 3 and 4, we'll say plus 3 space 4. And so this is how we'll add 3 and 4 together in Scheme. And I think we will use Scheme some. Again, it's a pretty as far as functional language, relatively important one there. Now, it comes from Lisp, and we'll see Lisp in the other textbook and talk more about that. So, again, talks about variables. We work a lot with lists of numbers and stuff like that in this. In fact, Lisp, the predecessor of this, was a list processor language. That's where its name comes from. And there are a couple of main functions we'll see. Char returns the first element in the list, and CDR, kernel, returns the rest of the list here. And then const will concatenate two things in the list. So if we have or add an element to a list, we'll add this element to this list here. And again, this comes from Lisp. It has old origins to registers and stuff like that. So it's weird, but we still have those around from the 70s, char and CDR values. When we get into more things, now we get into control flow. And again, we don't generally have a lot of like loops or things like that. We do kind of have a if-then structure for this, where we can have some condition and then some expressions there. But we don't, there is a for each on some of these, but again, a lot of functional programming will not want you to be doing the loops in it. And so we'll try to avoid loops when we do functional programming, because that's really not the way functional programming should be done here. And again, a lot of this revolves around lists and that sort of stuff. So, okay, so again, deals a lot with this book's scheme and that sort of stuff. So we'll see some more of this when we go through and look at some here. We do talk about what we call higher order functions. And you've already kind of seen these a little bit, like a function that takes another function as an argument. So map will take like a multiplication function or something like that as an argument. And so any function that takes other function is argument is called a higher order function here. So, okay, so we go through that now. The next thing we look at is logical languages. Before I go that, I'm going to jump to this other textbook and talk about their languages. Why are my links not working here? 620. I'm going to have to just jump here manually, it looks like. Okay. No, let's see. Okay, there we go. Jump up, and I'm just gonna go over this, the outline because I'm having trouble finding it here. So again, this introduces functional programming languages, starts talking about mathematical functions, and then goes into the first functional language, Lisp, there. And then from Lisp, it introduces Scheme, and then Common Lisp, which is a outgrowth of Scheme. Then talks about a couple more modern languages, Haskell and F#. Haskell and F# are quite similar there. We'll look probably at both a little bit. F# is relatively new. It's developed by Microsoft, and it is a functional kind of version. It's kind of named after C#. So C# was their kind of new language, their imperative language based kind of on C or Java, largely, I guess, on Java. And F# is really a Haskell clone, just like C# is a Java clone, but with some new things added to it here. But again, they mainly just introduced these languages and not a whole lot of concepts here. Then both books will go into logical programming and talk about what we call first-order predicate calculus here, and proving theorems and logical programming, and deal with really the only logical programming language really out there is Prolog, which has been around since I think the 70s. So it's a very old language here. And again, here's the logical languages talking about Prolog again, and how program is set up, and starts talking about some of the concepts, resolution, unification in these languages. And again, we're working with lists here with these languages. So, okay, so that's kind of how the textbooks introduce these. And we're going to now turn to AI and see how we can work with AI here. I suggest you go and open up under the discussion, the QQSP thing, open up the Unit 10 prompts document and make a copy of this and try out some of these prompts here. I'm gonna be working with the Gemini version of it. Again, since we have trouble getting Gemini on campus, I thought it'd be that one is something I could easily do. So under learning resources, I'm going to go over the Gemini responses to this. And again, I think we'll compare these with some of the other ones, especially when we run into some issues. So what are we going to be doing? Again, we want to probably be working with some AI models. So I've got ChatGPT. I'm just running 4.0 here in a window. And again, these responses here were actually generated with Gemini 2.0, whatever their new one is. We're also going to want to do some programming here. And so there's some windows I think you should open up. I'm going to open up a scheme window. Again, we've been using a lot of tutor points ones, but they don't have a scheme one. They do have a list one, which actually is very close you could use here. But there's a tryscheme.org that I think works pretty well. I'm going to open up a Haskell one, and I'm going to open up a F# one. So let's keep those. And again, Haskell and F# are very similar. I almost got rid of one of them, but again, they're both used a fair amount in these textbooks, and we'll try them out. I'll just warn you, the AI is really good at the big languages, and you've probably seen this in other places, but not so good at the less important or less common languages. And all these are certainly those. These are less common languages. And so we will see some issues with these stuff. So, okay. So we're going to set up our prompt, and I'm going to just paste this into OpenAI ChatGPT to kind of get me started, so it kind of sets the framework here. And I'm not actually going to do all these prompts today. Well, I have them all in Gemini, but I'll just do a couple. So again, what is functional programming languages? So it talks about what this is. Again, really, we're treating computation as the evaluation of mathematical functions. We avoid a lot of state stuff and what we call mutable data. These languages are good in that we can often use this stuff to prove kind of mathematically what we can compute and how, and what is computable. And we'll see this, some of this concept next couple of weeks when we talk about computational theory some more. So again, it goes over some of these things. We have most of these, I think, listed below, so I'm just going to skip over this for now. Languages. So Scheme is, again, a dialect of Lisp, one of the oldest programming languages. Makes me feel old when I remember I used to have a Lisp book, and I had a class we took in Lisp. So I didn't realize that I was studying, I first learned one of these oldest programming languages. So, oh well. So Scheme, Haskell, again, it's a purely functional programming language and strong types here. So we'll see that strong typing as far as variable types. And Haskell is really rooted in academic research for this. And it is used in a lot of schools and stuff like that. And F# is developed by Microsoft. Again, this is probably the most recent, certainly by far the most recent of these languages, developed by Microsoft for the .NET platform here. And it can be used for some of this stuff. I tell you, I don't know if F# is actually used that much. But again, it is the most modern of all of these. So I thought we should see that. So, okay, so what are our concepts here? And again, these are basically the concepts up here: pure function, immutability, that sort of stuff, first class functions. We're going to go through some of those. The first one we're going to do is immutability. So what does the term immutability mean to you? To me, it means something can't change for that. And so again, that's what we're looking at is once we create a data structure like a list, or basically once you create a variable or whatever and store something in there, you cannot alter that object. You can never, once you create a list, you can never add to the list, subtract from the list, alter the list in any form there. You simply will create a new list and do that. So that's what we're going to look at. And I decided to use Fibonacci numbers as a sequence. You usually don't use math examples that much, but again, when we get to this functional programming stuff, sometimes the math stuff helps. So if you're not familiar with Fibonacci numbers, again, we start with one, and then we can have another one, and it's just a sequence, and you add up the two previous numbers to get the new number. So 1 plus not 1 is 2, and then we add up 2 plus the previous number is 1, and we get 3. And then to get the next number, we take 3 plus 2 to get 5. To get the next number, we get 5 plus 3 to get 8. So it's always just the two previous numbers added together. And then we have these examples here in Scheme, Haskell, and F#. And this is where I think it's actually useful to try these out and try to figure out what these actually mean here. So I'm going to grab the Scheme example. I'm going to copy it. I'm going to go to my scheme.org window. You can do file editing on the right-hand side. But again, a lot of ours will be done automatically, and so we can paste it in here. We can paste this in here. Now, generally with Scheme, what you'll do is paste in a little at a time. So we would do, it's kind of, at least the way it's done here, it's done as an interpretive language for this. So like I would paste in this definition of a function. It would define that function. And then I would create a new list, define a new list. So I would paste that in here. And then I would define, that was my original list of Fibonacci numbers. So the list starts with 1, 1, 2, 3. And then I create a new list, and I would call this function new next Fibonacci number or list, and pass it in the old list here. And again, these define functions aren't printing anything out here. And then I'd finally I could display the original list. I could have, I guess, done that before. And then I can display the new list. But what I want to try to do is understand what there's this function, what does this code do? And again, this is where I think this is going to be a little hard for you to understand. Like this is our function definition here for this. And again, just the way it looks like here, I mean, it's somewhat similar to imperative languages, but it is, it's not like going from JavaScript to Java, I would say. It is a little bit different. Well, this is the format. So again, we work a lot with lists, and functions are lists here. So, and that's why we can treat a function as like we'll see in a little bit, as a first order object. We can pass functions around in the same way we pass lists around. So our function is always a list of things. So we say define the name of the function here and any parameters, and it's going to take a list for this. So we say when we call the function next fib list, we're going to pass it a list. So down here, this is when, let's see, when we define our new list, we will call our next fib list, and we'll pass in the original list. And we have defined the original list up here. So again, this is how we call this function is and again, we're used to saying like often a function name and then a parentheses and then the arguments. But again, we're using this prefix notation. We always say the operator or the function name inside the parentheses and then any arguments afterwards for this. So here's the function name. It's always the first thing in the list. And then here's and it only has one argument here. So that gets passed up here as the list again, with these if-thens, we'll say if, and then what we're testing for this stuff. And here we're actually testing or. So again, we don't say this or that. We say or, and then the two statements we're oring together. Again, we're using this prefix notation where we always say, like, rather than infix notation where the or would be in the middle, we're using prefix notation where the or is preceding everything. So we say or, and then we're going to check this, and then we're going to check this. So the first thing is just check if the list is null. Here is if the list is null, then that's true. And the other thing is we're going to check if this is null, and what is the CDR of the list for this. So remember, there's these in Lisp, there are these operators. Car gives us the first element in the list. CDR gives us everything but the first element in the list. And const is how we create add elements or add or create a new list from other lists here. So this is checking basically this is checking if there's only one element in the list, because if there's only one element in the list, then if we skip over that first element and do CDR for the rest of the rest of the list will be null. So this will be true if the list is null. So first we do that if statement here. Now, if that or is true, then we're going to do our cases. So if the list is null, we're going to return one list with just one in it. If it's not true, we're going to take the list and add one to the list. So this handles the case for the empty list or just a single item in the list there. Now, if that isn't true, so that if we do have a full list, we're going to define two local kind of variables, A and B. So A will be the first element in the list, and so we get that with the car. B will be the second element in the list. So how do we get the second element of the list? We do CDR on the list. So that gives us everything but the first element. And then we do car of the CDR of the list, and that'll give us the second element in the list. So B will be the second element in the list. And then we're going to take our list and append A plus B to the list. And again, this is the prefix notation, A plus B to the list. And we use this const to append items to a list, append whatever the first argument is to whatever list is in the second argument spot. The one thing I suggest when you're working with some of this functional things is you might want to be taking some of this stuff and asking AI about this. Can you explain this scheme program to me? And again, like ChatGPT is going to try to relate this to other things. So it's going to walk through, again, kind of like what I just said. What are all these things and what does it do for this? So again, that is Scheme, or a quick introduction to Scheme. Now, if you're kind of interested in Scheme, and I don't know, lots of people find Scheme and Lisp very cool. If you go to this tryscheme.org, there's a little tutorial here, and you can walk through some of this stuff with Scheme. So again, we can try out some of these commands, and this is just again basically an interpreter here we can just type in commands and see what that is. So again, we can say, plus, we can try minus 6 and 1 and try these out. So one thing I think is very useful is just to look through some of these examples or tutorials and then try to modify them to see like how do we can we multiply 6 and 2 together for that? And so they'll walk you through different examples here in the tutorial. And again, that's the README has the tutorial right there. So if you're interested in learning a little bit more scheme, that's fine here. I'm going to get rid of the tutorial right now. Okay. Let's do Haskell example. So again, I'm going to take this example. I'm going to go to my Haskell compiler here. Right now, it's got a print hello world. I'm going to, let's say I just put it after there. I'm going to get an error here. Kind of like Java, in Haskell, there can only be one main. So I have a main up here and a main down here. I've got to get rid of this main. I should have just deleted that, I guess, to start. And then I can run this here. Now, this is an example of where AI, this is Gemini, gets it wrong for this. So let's just walk through what this does. So Haskell is strongly typed. So again, we're going to define a function called nextFib list here. And again, in Haskell, what we always say is what are the types? It's going to take an integer as an argument, and it's going to return an integer. Not just an integer, the brackets mean a list. So it's going to return a list of integer or integers, and and we're going to return a list of integers. So we have to give it a list, and it's going to return a new list here. And then we do the cases. So we say next Fibonacci list, if the list is empty, and again, we just put an empty list there, then we're going to return a list with just one in it. If we call it with a list with only one item in it, and that's what X is here, then we're going to return, and here it's adding 1 to the beginning of the list for this. And now, otherwise, for a normal list, and again, this reminds me kind of a Python where you're kind of slicing your list up here. So we're going to break our list up into the first element, A, the second element, B, and then the rest of the list. And we're going to call that rest. So if it fits this pattern, then we're going to return a new list where we have the rest of the list. We have A, we have B, we have A, and we have A plus B to the list. So again, we're adding new elements to the beginning of the list here. We added 1 to the beginning of the list, whatever X was, and now we're adding A plus B to the beginning of the list here. And then here's our main. This is where we do our I/O. I/O has kind of always been weird in functional programming languages because they're not really built to do I/O like printout. So, but here we define, and again, we use the let command to do variable assignments in Haskell. And so here's our original list. But notice it has the bigger numbers towards the end of the list. That's going to be our problem. And now we're going to get our next list. So we're going to call our next Fibonacci with our original list. And again, this is just a function call. There's no parentheses. You don't say next fib, parenthesis, original list. You just say next fib, space, original list. And then we're just going to print off the original list and the new list here. And notice here's our original list, 1, 2, 3, 1, 1, 2, 3. But here's the new list. I would expect it to add 5 to the list here, but it is designed to add items to the beginning of this list. So it took 1 and 1 and added this 2 here. So this is where we're getting into trouble. It just didn't quite structure this. We're adding items to the beginning of the list. This list should be different. rather than 1, 1, 2, 2, 3, it should be 3, comma, 2, comma, 1, comma, 1. So the bigger elements should be on the left side of the list. That's how it's structured here. So now if we do that here, our new list is 5, 3, 2, 1 for that. But again, if you can with these languages, try to modify them. What if you want to add another element to the list? Can we do that? So what happens if we just like duplicate this line here? But this is going to add it to the original list. Can we just add the next Fibonacci to the new list? Will that work if we execute that? So, and again, it's going to give us an error because we're trying to change an object here. We assigned its value. We're using it now. We're kind of reassigning it. And again, we don't like to reassign here. What we're talking about here is that a lot of things are immutable there. So once we set a variable, we can't reset it for this. So maybe we call this new list A and new list B. And we pass new list A to next fib to get new list B. And we probably have to print that out too. Here's our new list. I'm going to say new list A, and let's print off new list B. And again, I think it's useful to try out these different languages, just to kind of play with them. I'll try to give you some simple examples and let you play with them a little bit here. Let's just quickly look at the F sharp example here. And again, Gemini gets this one wrong too. F sharp, I find, is a lot like Haskell for this. So again, right now we're just printing out hello world. There's the sample. We're going to put this in. So here's our next Fibonacci number. Again, we start with a list, and then we're an integer list here, and then we return an integer list. And here's the actual function. We're going to match list with match our parameter. If it's an empty list, we're going to return 1. If it's got a single element in the list, we're going to add 1 to the beginning of the list. Otherwise, if we can break it down to A, B, and the rest of the list, then we're going to again return A, B, and the rest of the list, but we're going to add A plus B, the start of the list. And again, when we execute this, it's going to do like before. The new list will put a 2 at the beginning. So really, we want to change this. And again, one difference here is that we're using semicolons instead of commas here. But again, we should say 3, semicolon 2, semicolon 1, and then do our list. Now if we execute it, the new list is 5, 3, 2, 1, 1. Here. And again, we can try to do this again. What if we try to add another element to the list? Try to do new list and take our new list and pass that in here. Can we do that? And again, duplicate definitions, the value new list. Again, these are immutable values. We can't reassign this. So again, we'd have to do like new list A and new list B, and then it would be fine. And then when I print this off, I'd have to print off new list A. And let's print off new list B2. Okay. So here's our new list. Now, one thing that I really like is, I mean, you have access to AI here. You can ask it to do things. So, I just did this, calling this. What if I wanted to try to print off the first 20 Fibonacci numbers using this? How would I do that here? One thing we don't often have in these is iteration. So again, I can go back here. Let's look at my scheme solution here. And maybe I want to ask AI that. So, can I use the following code to create or to display the first 20 Fibonacci numbers? So you should recognize that I have a function to generate that adds elements to that list, and it should want to try to do that with some sort of loop. So we can use that. We can use recursion. Again, we don't necessarily have a for loop. We have recursion, we'll see here. And so they're going to create a new function called next Fibonacci list repeatedly. So here's our code. Here's our original function. And then we're going to define this new function, generate Fibonacci's, generate fibs. It's going to take a list and then n the number of lists. So, we're going to say start with a list and generate the next 20 Fibonacci numbers from that list here. And so we'll see with recursion, we're going to check the base case. If n is 0, we're going to just return the list. Otherwise, we're going to call generate Fibonacci's recurrently. We're going to add the next Fibonacci to the list with our function here, and then we're going to subtract 1 from n for that. And then we're going to define our base case here, and then we're going to run this. So again, you can then take this function, bring that into your scheme compiler here, and see if it's going to work. And again, it generates a new list of the first 20 Fibonacci numbers. The next couple things talk more or less about actual programming and some of the concepts here. Pure functions. So what are pure functions here? So we want to avoid, pure functions are functions without any side effects. So we can't, inside a function, we can only access the arguments. We can't access there are no local variables or anything like that. There are no global variables. Everything has to be accessed just by the function. There are no member variables or anything like that here. So, and again, so always given the same inputs, the same arguments will always produce the same outputs. There are no what we call side effects. You can't modify global variables. You can't change the input parameters. You can't even perform I/O operations generally inside a function there. These are just pure functions. They're predictable, they're testable here, and you can run them concurrently. It's often nice you can break them up. So again, they talk about some pure functions in Haskell here and set these up. And again, we should be able to take these and just copy this to our Haskell interpreter and execute that code. So again, we're defining a function called add. It takes an integer it takes two integers and it's going to return an integer value. So we say add x and y are the first two integers, and then the result is x plus y. So then we can just call this function here. And it's very repeatable. There's no side effects. You can't add another value. You have to have everything in here generally. So we already talked a little bit about recursion, but recursion is used a lot here. We use what we call tail recursion instead of doing loops for it. So like, let's say we wanted to sum up a list, all the elements in a list. This is how we would do it in Scheme here. I'm going to do a new. We're going to define a new function called SUMList, and it's going to pass in the list. If the list is null, the sum is 0. Otherwise, we're going to add the first element of the list. So again, car gives us the first element in the list in Lisp-like languages. And then we're going to recursively call sum the list, this same function, with the rest of the list. So CDR returns everything but the first element in the list for it. So this is the recursive call that will add the first element to the sum of all the elements in the list. So now if we say sum the list here for this. So again, no loops, but this is what we typically do in a loop sort of stuff. This is just a recursive function call here. And again, we can see that in Haskell. Let's do the F# version. I'm going to skip the Haskell version of it for now. So again, we're defining a sum list. We're giving a list here, and it's returning an integer. So it's given a list of integers. So one thing that I think makes F# a little easier for you to understand is that the way it defines functions is what you're used to. We give it a function name. We have parameters in parentheses where the type of the parameter is there. And then we say colon, and this is what the function is returning. I think that kind of notation that F# uses is what you're used to from imperative languages. So then again, we're passing in a list. We're doing a match on the list. If it's an empty list, the sum is 0. Otherwise, we break it up into the head and the tail of the list. The first element is the head, so we take the head and we add, and now we'll say call SUMList on the tail. And again, this is our recursive call. So this makes this a nice, simple recursive function to add up all the elements in the list here. So when we get down to the empty list, it's 0. So when we call this, and again, we could ask, sometimes it's nice to see, someone walk through this. So can you walk through or unwind this recursive example in F#? So again, it walks through what we're doing here for this, and it kind of shows the list. So again, we're first call SUMList with the whole list, 1, 2, 3, 4, 5. And then we say, okay, now we're going to say 1 plus SUMList of the rest of the list, 2, 3, 4, 5. And then we're going to recursively call 2 plus SUMList with the rest of the list, and so on. Eventually, we call SUMList with an empty list, and we know that's 0. And then we can do all this math to get up to 15. So again, when you're looking through these examples, and again, when you're doing it, you might get different examples, although I tried to push some of these. I told it to do an example of summing items in a list, I think here. Yeah, some of the elements in the list for this. And again, this just kind of shows how we do this iteratively in Java, we'd have a for loop. We'd loop through and do this sum. And this is how we're going to do it, how we do it in F sharp. So it is quite a bit differently because we're forced to do recursion. Because really we don't, in most functional languages, we don't have loops for this. I mentioned earlier a little bit about first class functions. So remember, in higher order functions, so all in functional languages, functions are first class, meaning they get treated like anything else here. They can be assigned to variables. We can pass them as arguments to other functions. They can be returned. You can have a function return a function. You can store them in data structures, all that sort of stuff. And then a higher order function is any function that takes one or more functions as an argument or returns a function as the result here. I like scheme because functions are just lists here. And this is where list background comes in, where the data structure, the primary data structure is a list, and functions are defined as lists. So functions are always like this stuff. So here's a function. And again, we could take this and bring it into our scheme. So we define an add one to an element, so here's our list. We're going to then define a function called apply. We're going to pass in a function and a value, and then we're going to apply that function to that value. So basically, we'll pass in a function and we'll apply it to that. And now we're going to call apply function. What are we going to do with it? We're going to pass in the add one function we defined up here, and we're going to add 5 to it. So this is a very complicated way of adding 1 to 5. So, and then this will go up here and apply this function to and send it 5 here. So we can, and it creates 6, but adds 1 to that. And again, where you probably run into this is you see, we looked at map and filter and reduce with lists. And those are kind of where we pass in a function or a lambda function to those functions to like apply the same function to every element in a list or something like that. Just gonna mention, because again, if you get into some of the theory of this, you get into this function composition here, where I don't know, maybe you're used to writing, I'm trying to remember I don't know what math background you have, but if we have a function g and a function f, if we want to apply g to some value x, and then we can apply to f to the result of that. So we can say f of g of x here. And another way of doing that is we can do this. We can do composition f composed with g creates a new function, and we can apply that to x here. So if you go into some of the research or theory of functional programming languages, sometimes this composition comes up. We can also do these pipelines where we apply functions. So a lot of times a function will return a list, and then we can call that function again. You'll see this, well, it's not exactly the same. Sometimes where you will be able to call a function or on a object like a list, and then call another. Like if you have a string, you can say like string dot to upper, and that'll return a string, and you can say dot to string or something. You can do a number of operations on that here, and that comes from this sort of pipeline operation where we can say x and we can add 1 to it, and we can multiply it by 2, and then we can square it for this. So we can create kind of a pipeline of functions that are applied to this. I'm not going to go into too much detail on that, but it is used somewhat in these examples. I will mention lazy evaluation because that is another concept here. So most of your languages often will do eager evaluation like Java and C#. If you pass in like something in as a argument, you say like x plus 4, and you pass that as an argument, it will do the x plus 4 and then pass the result as the argument here. We do eager evaluation. If we can evaluate an expression, we will evaluate it. Haskell and some of these do lazy evaluations. They'll pass that as a function and evaluate it later. It also lets them, Haskell has this weird thing where it can have infinite lists here. So again, in normal languages, you cannot have an infinite list of numbers or things like that. But in Haskell, you can, and there's a notation ... for that. So you can create an infinite list of like natural numbers here. And then you can work with that infinite list. You can do operations on it, and it'll only do them as needed here. I don't really see the value of it. I mean, I understand lazy evaluation sometimes because it can optimize things, and if we're not going to need to do that calculation, we don't have to. But as far as these infinite lists in Haskell, I really don't understand why they're used that much. But it just, I mean, again, a lot of this stuff is used in our academic research sort of stuff. So I imagine it has a good home there. So both logical, I mean, functional languages and logical languages and functional languages have kind of an underlying theory that predates them. So for functional languages, the underlying theory is lambda calculus. And lambda calculus is based on lambda expressions. We actually have seen lambda expressions. So it's, in general, lambda expression is like an anonymous function, although in a lot of these languages, it's a function and it's just called lambda often, rather than, so I'm going, that's not anonymous, but in a lot of other places, they're kind of a function defined on the fly here. So here's our scheme example. Let me grab that and put that in here. Let me see if I can get this right here. So again, we're going to define a lambda expression x, and it is going to take with one parameter x, and it's going to take x and add 2 to it there. And now we're going to apply that lambda to x 4, 5 to generate some outputs. So again, you're somewhat familiar with these lambda expressions from other languages here. So I won't go into these examples too much, but I want to get to the lambda calculus here. So this comes from the 1930s, which again predates most computers and stuff like that, long before electronic computers, like they say. So lambda calculus has a different notation. So we have variables, like you see. We define lambda, and again, this is where it comes from, is we use the Greek symbol lambda, and we define the name of the function dot the arguments to that function here. And then, I mean, the name of the function or the first parameter, and then the result of that. So lambda, if we see x, we're going to change it to x plus 1 here, basically. So if we have this expression, lambda x dot x plus 1, so again, this is before, you know, like would be maybe the argument or the parameter, and this is the return value. And the period separates the two in this sort of calculus or expression. So now if we have that expression, and we apply 5 to it, it's going to generate 6 for this. Now, in a lot of our languages, the lambda symbol is replaced by the word lambda, like in Scheme, or in Haskell, we replace it with a slash. In F#, we replace it with the function definition here. So, but you can do a lot. I mean, there's this whole area of lambda functions and how they work. So, like, this is the identity function here, lambda x dot x. So if you're given x, you're just going to return x. So if we say lambda x dot x y, we're applying y, giving y to this function here, and it will just return y for this. So now we can do things like look at longer examples like lambda x, lambda y, lambda z of x, and then y and z here. So here we're going to take z to be a list. We're going to apply a list of numbers to that. And now y is going to add 1 to each number in the list. And then x is going to double each number in the list. So we can create this expression where we can do this and do this more complicated example to a list. If we start with a simple list like 1, 2, 3, we can generate more complicated versions of it. Now you're saying, Tom, this looks really interesting. I wish I could spend a whole week learning lambda calculus. Well, you can in your final project if you want. So again, I'll probably next week, maybe on Thursday, we'll start talking about the final project and a research paper, and you can delve into something like this. So again, a lot of times I'm just going to introduce some concepts like this where there are whole, books written about lambda calculus here for this. So, and you can decide if you want to learn more about it. So in lambda calculus, one thing we do is we look at complex formulas or functions, and we reduce them to what we call a normal form for this. And we have some ways of reducing some things. So if we have like this expression, lambda x dot x plus times 2, so we're taking x and multiplying it by 2, we're passing 5 into it. The function is this, the argument is this. So as our normal reduction, we can just take 5 and put it in here and reduce it here. So basically, this reduces to just 5 times 2. We're just substituting the argument for x here. And then we just get 5 plus, and then we can evaluate that, and that evaluates the 10 there. So this expression reduces to this. And again, sometimes it just means applying the function. Sometimes it means if this is y, some other expression here, can we reduce this? Can we substitute this in and get a different expression or have a different example for this? So like this is maybe a better example here where this is not just a substitution, but this is like a function being passed into another function sort of idea. Now, sometimes there are questions on should you do things in this order and this order, and there's a theorem that ties this all together, meaning saying that the order of operation is really not that important there. So basically, if there's 2 ways to reduce an expression and you get 2 different results, there's got to be a way you can reduce both of those expressions to something that's identical. So in the end, as you reduce things, You might take kind of different paths or apply things in different order, but at the end, the results are always the same for this. So did you like this introduction to the functional programming languages? Again, it's interesting. It gets you, hopefully it tries to get you thinking a little differently. I don't know, I think if you have had a lot of calc and math, I think these functional programming languages make sense. I kind of like, I think it's kind of interesting that Scheme uses this prefix notation. When I was growing up, we had these things called calculators where you would, they're actually physical calculators, and you type in expressions. And one of the big calculators out there was made by a company called HP, and HP used prefix stuff on their calculator. So if you wanted to add 5 plus 2, you did not on your phone calculator, you say 5 plus 2 and you get it. But on HP calculators, you always said plus 5, 2, and would add those two together there. So it does show you that different kind of notation. Let's talk about the next thing is these logical programming languages here. These are even more different, I would say, than functional programming languages. But there's really only one example of this, and this is Prolog. And here, so let's review this. So again, logical programming languages are based in logic. We focus on what the problem is, not how the problem will be solved for this. Sometimes people talk about SQL being that way too. You just say what you want to do, not how it should do that. Is a declarative language, not an imperative language for this. But in here we have facts, we have rules, and we have queries. We then use some tools, unification, resolution, and backtracking to apply the rules to the facts to try to find the answer to the query. So first you describe the logic and the relationships using facts and rules. You set up this whole logical structure. And then you can ask questions of the system, and it will look through all the facts and the rules and figure out the results of this sort of stuff here. And here's our example in program. Oh, I forgot to check. Do we have a Prolog interpreter at Tutor's Point? Yeah, did I put that at the top? No, I forgot to put Prolog up there. Okay. But Tutor's Point has a Prolog interpreter here. Not getting this to copy. Yeah, okay. So here's our example here. We define some facts for this stuff. So we say John's parent is Mary, and John's other parent is Peter. Susan's parent is Mary also for this. So again, those are facts. Those are kind of statements here. And statements are usually in terms of relationships or kind of these functions, often called ISA. So yeah, relationships here. And then we can define functions here. What are they? Yeah, rules, I guess, is what they're calling it. So we can define these rules. A sibling is if X is a sibling of Y, if the parent of Z, if you can find a parent where we have Z and X, and another parent where we have Z and Y, where X is equal to Y here. So you can find two people with the same parent here, then they're called siblings. So we define that logical relationship here. And then we can ask some questions. We can ask, are Mary and Peter siblings here? We execute that. I think we just want to do that. Sorry. And it should, I'm not sure why it's not printing that out for us. So it should return true that Mary and Peter are, let's see if that, oh, yeah. I don't know if this example is right, because to me, Mary and Peter, yeah, are husbands, or unless maybe this is the other. I think I was saying the parent right. So John is the parent of Mary. John is the parent of Peter. So then Mary and Peter are, yeah, are siblings. That's what we're doing. So the child is always the second one, and we have the same parent here. And then we can look at Mary and Susan. So Susan is the parent of Mary, so they're not siblings. It should turn false here. So walk through different examples here. We can define relationships like parent. We can like have likes or other relationships like Mary likes chocolate here. We can have these variables here. We can run these sorts of clauses for this. And we use this. Our assignment statement is this colon dash stuff. So we can assign, so siblings is equivalent to this statement. And then we can write queries. Yeah, that's what they were trying to do. Why didn't this query work earlier? Go back up here and see. Yeah, it's not, I don't know if that, I haven't tried out this prologue one and this one, so I'm used to just running kind of through in my head. So we can also define lists and membership in the lists. So again, we can say like, we can ask, is A a member of this list or is D a member of this list? So A is a member of the list, D is not a member of that list here. We can also ask like, what are all the X's where X is an item on the list, and it will try out find all the possible solutions where all the possible X's for this. So. Now this works. How does this find the results? It uses something like called unification. We find all sorts of variable substitutions. We try all sorts of variable substitutions or combinations that will work for this. So like with this, well, let's go to this here. Oh, we might have lots of parents and combinations here, and then we have this rule here, and then we ask, is parent of or is sibling John Mary? That's what I want to ask actually here. And it will say, well, I'm going to try every parent here and every parent here and try out every possible combination. So we'll try with this John and Mary as this first parent, and then try John and Peter as our second one. And then we'll try every combination of parents in here and see if this comes true for any combination. And if it works for some combination of facts, then we know it's true. But unification will try every combination generally for that here. So in simpler terms, it's about matching the assigned values to variables here. And so it tries to look through and find matches for this, and it walks through some examples of this. So very much this goes of idea of pattern matching. And again, resolution is tied to the same thing. We can sometimes derive new clauses from existing clauses. So if we have two clauses, this is true like A or B and not B or C here. We can devise a new clause using logic for this from this sort of example. And again, we'll get into predicate calculus in just a little bit, and that's the foundation of this. And there are rules in predicate calculus how you can combine different statements together to make new statements. So sometimes we're given some statements here, some rules, and we can't, in unification, we can't find the right substitution for rules. So then we can use resolution to generate new rules from previous rules using predicate calculus, and then try those new rules on our system to see if we can unify it. And again, that takes lots of kind of searching, kind of like a tree search, and backtracking is how we search it's a systematic approach of all possible solutions to a query. It tries the first clause, it fails, it backslacks. Every time there's a choice where you could decide should you do this or what, it creates what kind of like a branch point and a save point saying, I made a choice here. Eventually, I have to come back and try the other choices here also. And again, we're basically doing a depth first search through all the combinations here. So it kind of walks you through this sort of situation where, again, we have these parents, we have this sibling relationship, and we want to know does Mary have any siblings? Why? And it searches through and finds that there's only one sibling Y or if Y is Peter, we'll see if Y is Peter, we'll see if that's true or false, basically in this. So it kind of walks you through all the different steps that it does to try to get to this idea. And again, I mentioned lambda calculus in here for functional things. First order predicate calculus is again something's been around for a long time here, and that's what we use for this. So in first order predicate calculus, we have predicates, things like John likes Mary, or John's parent is Mary. Here, or I think it's the other way around. Mary likes John. Mary's parent is John. 3 is greater than, or 5 is greater than 3 here. And then we have objects or variables here, and we can then map. We have functions. We can say like, who is the father of John, and we'll or the parent of that. Once we have this, we can write these quantifiers for all, and there exists like for all x. We can say, is there an x that is human? So for all x, is x a human? So basically, I'll look through every, like maybe a list of objects or whatever, and or possible values, and this is only going to be true if every x is human. So that's what the for all means, is we have to apply this to every x here. And there exists is the opposite. Oh, I don't know if we call it the opposite. So we want to know, does there exist an x where x is the parent of Mary? So this will try to look through all the possible values and see if there is at least one case. So this will be true if there's at least one variable that we could substitute in here that would make this true. And this, the for all, is true if every variable, every value we assign to x, this would be true. So, and then we have our logical things. We have our ands and our nots. We have a negation, and we have implications, kind of an if-then sort of stuff. And we can write statements like there exists a person who likes chocolate. Like there exists an x where x likes chocolate. Here is we write that. If someone is a parent, then they are human. So we could write that out. For all x and for all y, if parent x and y, then is human x. For every number greater than 5, it's also greater than 3. So you can write that sort of statement out. No dogs can fly. So you can write these sorts of statements out in first order predicate logic here. I'm going to skip over the rest of this stuff. Soundness and completeness, that's what I want to. So first order predicate calculus has been around for a long time. And again, it is sound and complete, meaning like this obviously, if you prove something is true in first order predicate calculus, it is kind of then true. And any statement that is true under the facts, you should be able to prove with first order predicate calculus. So it is sound and it is complete here. And Gödel's completeness theorem for first order predicate calculus states that so for any sentence in first order predicate calculus, if it's a logically valid sentence, then our first order predicate calculus is provable, or our statement is provable within that. So if it's logically valid, you can prove it in first order predicate calculus. You can't come up with sentences or statements that you can't prove under first order predicate calculus. Now, you may be familiar with Gödel's incompleteness theorem, and you're thinking, I thought it was the incompleteness theorem. So first order predicate calculus is complete. Anything above first order predicate calculus is incomplete. So you can't do arithmetic in first order predicate calculus. It's just a logical system. So anytime you add arithmetic to a logical system and define arithmetic there, adding and subtracting, for example, then you can generate statements that are incomplete. So that, if you're familiar with Gödel's incompleteness theorem, it applies to systems that are above or more complex than first order predicate calculus, but generally like arithmetic, because his theorem relies on infinite sums, or if I remember correctly, something like that. Sets of where you add values to it. Okay, so try some of these things out. Post your QQSP to the discussion area by Thursday. We've been forgetting to do discussion, so we'll actually try to do a little discussion on Thursday on this, and then we'll do the learning activity here. Again, the learning activity, I haven't finished it up, but it will be similar to like the past ones. We'll probably look at 3 different functional programming languages and have you try out a number of examples in these functional programming examples and run them and do that sort of stuff. So we'll do try to learn one functional programming language a little bit for Thursdays. Okay. Sorry, I talked a lot today. Online people, any questions?